The second session of the second session of the second week of the summer school is really a placer and honor to introduce Marco López de Prado. Marcos is a professor in Cornell University, a research fellow at the Lawrence Berkeley National Laboratory, and responsible of the study of artificial intelligence investment in ADIA, and also advisor fellow of ADIA. Really, Marcos was the person that promoted, together with the team, the director of ADIA, Horst, Amelie, helping us promote the organization of the summer school. And this year, fortunately, he's here. Sorry, because we move from tomorrow to today the talk of Marco, because Marcos must going back this afternoon, was the reason that we introduced the additional talk of Marcos, and we move the remaining session. Marcos really says well-recognized research in the area of AI and finance, one of the leaders around the world, with several important influential books, and he received several recognitions, among them the Knight Officer of the Royal Order of Civil Merit of Spanish government. Really, it's a pleasure to introduce him, and directly the slide, this is Karma's slide, we must change to your slide, and he will introduce us about causal AI and the use and the importance of the problem of causal AI. Thank you very much. We need to. This is the slide of
oh, maybe this. Tenemos que cargarlas, supongo.
¿Pero las has enviado?
Sí, las envié ayer. Ahí está, eso es, el segundo. Ahí está. Muy bien. Ahí está, perfecto. Ups, de ahí sí, ahí está. Ahí está. Sí, déjale, lo hago yo. Sí, lo hago yo. Ahora sí.
Okay.
Vale, gracias, Paco. Good morning. Thank you, everybody, for coming. I'm going to talk about the missing link in artificial intelligence in order to develop trustworthy applications. So we are all very familiar with various uses of AI in society, self-driving cars, face recognition software. We use it every day, including ChatGPT. And those are wonderful applications. There is nothing wrong with them. However, when we need to apply AI to certain use cases that require trustworthiness, we encounter a roadblock. So what does that mean, that an application is trustworthy? Well, it means many things, but let me summarize or highlight a few aspects that are required for an application to be trustworthy. One of them is that results must be explainable. Explainable means that we understand why the system made a decision. Not only that we understand that it made the decision because we fed some data and something came out, but what are the mechanics? Why a decision was recommended as opposed to a different decision? So we are able to understand the process, the logical process by which this application made a particular choice. So that's one very important aspect of trustworthiness. We would not typically accept a recommendation where we have no idea why this particular course of action was recommended to us. Well, when we use a self-driving car, the algorithm makes a number of decisions, turns left, right, and we have no idea why. We may trust the application in the sense that it usually gets it right, but the day that it gets it wrong and someone gets injured, we would like to understand what went wrong so that we can correct it and improve it. Well, this is something that, this is where causality comes into play. It's the missing link between AI and trustworthiness. I'm going to talk about trustworthiness from the angle that I'm most familiar with, and many of you are familiar with, and which is investing. But a lot of what I will explain today applies to really any situation where we require trustworthiness. And during the presentation, I will make it clear why investing actually is a very interesting example of the difficulty of these systems to be trustworthy. One difficulty is, as you know, there are billions of people on this planet who can drive cars. And there are billions of people on this planet who can recognize faces. But there are not billions of people who are able to beat the market. So it is a very challenging and arguably one of the most challenging data science problems that one can encounter. How to predict the markets, how to beat the collective wisdom of the crowds. And the fact that it is so difficult makes it a very interesting case. Meaning that if we were able to crack this problem for investing, probably we would be able to crack the same challenges for applications where we have millions of successful users or millions of successful judges, if you will. So why investing matters? Well, investing is the allocation of scarce resources with the expectation of future benefits. Nobody invests if there is no expectation of a profit. And the same could be said of many other applications of AI. You want to use the application because you expect that something good will come out of it. An allocation decision is made under high uncertainty. And that's something that, as you will see, will make it very, very challenging. The decision to turn a car left or right doesn't occur under high uncertainty. You know that if you steer the wheel left, the car will go left. Now, whether this was the right decision or not, that's a different point. But in investing itself, almost every aspect of investing is shrouded in high uncertainty. You may want to buy a security, but you don't control the price. And if you try to control the price, you don't control the volume. So there are many aspects of investing that are highly uncertain. Efficient investing is essential for prosperous, self-reliant, and sustainable societies. We should vanish the thought where investing is something that only greedy people do. In fact, investing is essential for the well-functioning of society. Let me show you a few examples. In this plot, you can see on the x-axis investment as percentage of GDP, and on the y-axis average annual GDP growth. And something remarkable about this plot is that the US and the EU invest roughly the same percentage of the GDP, assign the similar percentage of GDP to investing. It's around 23-24%, but look at the disparate outcome. What the EU gets out of that massive investment is around 1% GDP growth, while the US gets around 3%. Why is it that two economies that are both developed economies, both have access to similar access to education and services, etc. Why is it that one economy achieves 3 times the output compared to another? Well, it has to do with efficient investing. This is really what the US economy is really good at. You are able to make investment decisions, and if the investment decisions are right, you are rewarded, and if they get wrong, you get punished and penalized. And there is greater transparency in these decisions. There's greater access to information. There are a number of aspects that make investing more efficient, meaning that for the same input you get higher output. Look at Japan. They invest more, but somehow they get almost zero growth. It has to do with many aspects. I don't want to to reduce everything to investing, but definitely efficiency in investing, but definitely investment efficiency plays a huge role in determining outcomes. In the case of China, you have 40% of GDP assigned to investing, and you have a spectacular outcomes. It's around 5% growth.
Marcos, if I read well your, and forgive me to interrupt, but in my humble opinion, there is two outliers in this picture. One is Japan, of course, and the other one is Brazil. But in that case, I believe that depending of the local aspect, Brazil has a very young population and have a lot of natural resource that can help with a few investment to have a high profile. And Japan, it's probably because they don't have these two main features, characteristics, and also because of the culture of Japan that can be complicated to in this moment. I believe they need a new approach, and they need to change completely the behavior of them.
Yes, you're right. As I said, I do not want to reduce everything to investing, but there are some interesting observations that one can make on this plot without being assigning everything to investing. But definitely the case of US and Europe is quite remarkable.
But even in our case, as you know, our approach to investment is culturally is completely different.
Yes.
It's also made, I believe, the difference.
Yes, absolutely. And this will link to part of the slides where we will talk about confounders and other effects and how to make attribution. But what I want to take away from this plot is that it is not true that growth is just a function of how much you invest. How much you get out of investing has to do with how efficiently you do the investing. Very good. Now, investing has gradually become a data science problem. There was a time 80 years ago that investing was truly more of an art than a science. There was no data. There were very simplistic mathematical models applied, essentially averaging. There were no computers, no financial theories. It was truly decision making based on stories and themes. Around the year 1950, there was a first revolution whereby some academics started to develop the theories for what makes an investment efficient. And that's where the capital asset pricing model, asset pricing theory, risk factors, Black-Scholes, market microstructure, modern portfolio theory were developed. It took around 50 years for a lot of these ideas to propagate and to start to impact the industry, and that led to the development of mutual funds and exchange-traded funds. Stock picking became more of a way of investing, but not really the core. So today, most investors are not stock pickers. They invest either in risk factors or in the broad index, and this is really the result of these theories taking hold. Around the year 2000, technology came into play. That's when data storage, supercomputing, networking became much cheaper and accessible, and that led to high-frequency trading. And it's around the year 2015 when machine learning enabled a third wave of innovation, and that's where alternative data sets, valuation, forecasting, nowcasting begin to be the new drivers of development. So as you can see, over the past century or so, we went from a way of making investment decisions that was very heuristic into a way of making decisions that is primarily driven by data and mathematical models. Now, it would be erroneous to think that investing is simply a forecasting problem. It is not, and let me explain why. Suppose that you are able to predict the price of Amazon, and you predict that the price is going up and you want to buy Amazon. Now, you want also to diversify a bit of the risk because your prediction is not perfect. You may want to build a portfolio, and you will want to build a portfolio that includes Amazon and stocks similar to Amazon and perhaps other sectors. So now you need to make an investment decision that is based on building a portfolio. Now, when you build a portfolio, you need to make an allocation to the various constituents of that portfolio. So now you're forecasting Amazon, but also Meta and Netflix and a number of stocks, and you need to take into account a covariance matrix, right? You need to incorporate information about the correlation between those assets. And you will want to hedge certain risks. You do not want to invest too much in Amazon if at the same time you're investing in, let's say, Meta. So now you need to control for certain risk exposures. This means that in order to build an efficient portfolio, you need to attribute, you need to make an attribution of expected returns to risks. And that's really what portfolio construction is. When you use a model like Markovich optimization, convex optimization, you need to make a mapping from the risk factors, the risks that you are taking in your portfolio, to the expected returns. And that's really what efficiency is, right? Efficiency is, given that I take these risks, I need to be rewarded for those risks. If I'm not getting reward for a risk, that is inefficient, because it's a risk that I could have avoided altogether. That's the key why causality is intrinsic to investment efficiency. Only a causal attribution of risks to returns enables us to obtain a portfolio that is efficient. You could have portfolios where you take certain risks and they appear to obtain a certain return, but unless you know what is the exact attribution of returns to risks, you cannot optimize the portfolio. Now, this causal attribution must be done under uncertainty. We do not really know exactly what is the correct attribution. We can try to infer it, we can try to make a mapping, but it will still be with certain degree of confidence. And there will be interaction effects between the risk factors, right? So that's exactly what a causal graph tries to represent. How are these variables interconnected to each other? So let me give a very simple example of what this means and why forecasting is not enough. Suppose that we would like to model the consumption of ice cream consumption and drownings. We observe in the data that actually they are very highly correlated. They are highly correlated. It's true. You can search that in the internet. Ice cream consumption is very highly correlated to drownings, and the reason is rather logical. It's weather. When the weather is hot, people tend to go to the beach and engage in water sports, but also they tend to consume more ice cream. Now, that means that I could use a machine learning model to try to predict drownings as a function of ice cream sales. and the model would be actually quite successful in making that prediction. Does that mean that I can control the risk of drowning by controlling ice cream sales? No. There you have it. You can have a model that is very successful in forecasting drownings, and yet is not helpful in managing the risks of drowning. We could ban ice cream sales, and that would not reduce the number of drownings. Perhaps it could even increase, because maybe more people would go to the beach to try to cool down. So I think that this is a very obvious example of why forecasting is not the same as controlling risks. And why forecast? You could have a model that is very good at forecasting, and yet that forecasting capability doesn't translate in efficient investing. And the same example will happen with many other applications where you need to control risks. Think of, for instance, medical treatments. You could have a treatment that, or you could have a symptom, right? You could have a symptom that is very highly predictive of a condition, and yet you try to deal with the symptom, and that has absolutely no effect on the condition. You could still be sick even though you are dealing with the symptom. For instance, with the flu, right? The typical treatment of the flu is you take a certain paracetamol and a number of decongestions, etc., and that deals with the symptoms, and yet it has absolutely no effect on the disease. You still have the virus. It doesn't reduce the amount of virus in your body. It only reduces the interaction of your virus with your immune system. So this is where causality comes into play. Causality tells you exactly what variables you need to interact and intervene in order to deal with the condition or with investing, with the outcomes, with the effects. Is that clear? Any questions? Good. So this is a visualization of what happens when you have a very simple causal graph. You have a variable x, let's say it's a risk factor, like value, momentum, quality, yield, low volatility, liquidity. You can have any of these risk exposures. These risks are supposed to be rewarded. And then you can have a variable that is called a collider that is influenced by both the cause and the effect. And if you have a causal graph like that, and you confuse the role of z in the graph, meaning that you think that it is also a cause, if you get the direction of this arrow wrong, what you will encounter is that a small change in the value of that delta parameter can make the strategy generate systematic losses. So even though you have a model that is very good at forecasting, because of the way your risk model hedges, it ends up printing losses. So again, this is another way, perhaps a bit more rigorous way of showing you that investing is not about forecasting. Forecasting is part of investing, but is a necessary non-sufficient condition for investment efficiency. And I think that this is something that many people get wrong. I'm quite sure that if I were to ask 99% of investors whether investing is about forecasting, 99% would say yes. You just give me the best forecast, I know what to do. And they could not be more wrong. You could get great forecasts, but you need to build a portfolio to control some risks. These forecasts are not 100% guaranteed, right? There is a risk associated with every forecast. This means that you need to manage risks. And the moment that you get into risk management, depending on the biases in your model, you may be hedging risks that are rewarded and not hedging risks that are unrewarded. Okay, so we need to separate two very important concepts, association and causation. Forecasting is all about association. It could be also about causation, but definitely it's about association. In order to have a good forecasting model, you need to get a good model for associations. But causality is something different. And it has taken around 2,000 years, at least, for people to figure out what causality is. You can go back to texts of Pliny and other Roman and Greek authors, and they talk about causality. Even poets in Rome wrote poems, works of art, where they talk about causality. So it has been in the minds of people for a long, long time. But for 2,000 years, people struggle with what causality is. We all have an intuition about what causality is, but one thing is to have an intuition, and another thing is to have a formal mathematical definition of what causality is. And today you are going to hear that definition. And it will make sense, I think. But first I need to introduce a couple of very simple concepts. The first one is the concept of a data generating process. A data generating process is just the system of equations that generates the data. So this can be visualized with a graph. That's exactly what a causal graph represents. You have some variables, x, z, y, for instance, and then you have some arrows. And the arrows tell you what variable influences what. So z influences x, x influences y, z influences y. All right, so you can already think of three equations that have that topology, that have this way of relationships among them. Okay, so that's the first concept. You have a process that generates the data, and the interactions or dependencies between the variables can be represented through a graph. The second concept that I need to introduce is the concept of a path. And a path is just any sequence of arrows between two variables. You pick two variables and you can reach those variables crossing those bridges. Now, when we talk about paths, we do not care about the direction of the arrow. We just care about the arrow as a bridge. And the bridge can be crossed left or right. It doesn't matter. That's why we call it a path as opposed to a directed path. A directed path must follow the directions of the traffic, right? For instance, a directed path between x and y, there is only one, and it's through bridge number 3. That's the only path that allows me to go from x to y while respecting these rules of the road. However, if I am allowed to follow any path, directed or not, then I could reach between x to y. I could go through 3, or I could go first through 1 against traffic, and then through 2. All right, and that's what is called a backdoor path. It's a backdoor because essentially I'm using the indirect way to reach y from x. Okay? Okay, so that's the second idea that I needed to introduce. Data generating process, paths. And now the third and final idea that I need to introduce is block path. Paths can be blocked or unblocked. Let me show you this with this diagram. In this diagram, there are variables that have different roles. A variable like z can have 3 different roles in this graph. Number 1, it could be a confounder. And a confounder, what it means is that z influences x and y. So in this graph, there is a confounder, w. W influences z and y. That would be a confounder. W would be a confounder to z and y. Okay? then there is a separate role a variable could have, and it's a collider. And in a collider, the direction of the arrows are flipped. So a collider would be when two arrows collide against one variable. Z is a collider in this graph. And finally, a variable could have a different role, and that's a mediator. A mediator is something that just stands in between. Z is a mediator between X and Y. Okay, so think of variables can play three different roles. And depending on the topology of the graph, you can find colliders, confounders, and mediators. Okay, so now that these three different roles are clear, I'm going to state a theorem which I'm not going to prove, but it's a very important it's the most important theorem in the entire presentation. And it probably makes sense to some of you, but the proof is a bit convoluted. So let's take it as a proven statement. We don't need to understand the proof to use it. The reality is that this has been proven. A path between two variables, X and Y, is blocked if one of two conditions happen. So possibility number one is the path between X and Y is blocked because the path traverses a collider, meaning that two arrows collide against one variable, and the researcher has not conditioned on that collider. So you have a collider, like in the case of Z, and we do not condition, meaning that we do not put it as an explanatory variable in our regression, or we do not put it as a predictive feature in our model. So when that happens, Z is a collider and is not part of our X matrix, the path is blocked. Possibility number two is the researcher conditions on a variable in the path between X and Y where the condition variable is not a collider. Okay, so a variable can be a collider or not a collider, right? It's a binary choice. If it is a collider, the path is blocked if we do not put it in the matrix of predictors. And if it is not a collider, the path is blocked if we put it in the matrix of predictors. And this has driven people very, very confused for hundreds of years. It really took until recently that this duality was understood. Depending on the role of the variable, we may or may not need to control for it. And if we make the decision wrong, we're going to get the opposite of what we wanted. Meaning that we wanted to block a path, and if it is not a collider and we didn't add it to the features, then the path is unblocked. If it is a collider and we add it to the features, then the path is also unblocked. So you can do, depending on the role of the variable, doing the same thing can have opposite outcomes. Okay, so now we can finally use these tools, these three tools, data generating processes, path, and block path, to separate once and for all the concept of association and causality. Association is very simple to define. We all learn it in the first course of statistics. Two variables, X and Y, are independent if the probability of one condition on the other is equal to the probability of is different of the probability to the first one. Then, in that case, the two variables are associated. So when conditioning has no effect, then the two variables are independent. All right. So what is the probability of what is the probability of you having an accident? No, let's not take a grim example. What is the probability of you being thirsty conditioned on doing exercise? Well, doing exercise actually has an effect on being thirsty. So the two variables are clearly not independent, right? And that would be determined by this, right? The probability of being thirsty conditioned on doing exercise is not equal to the unconditional probability of being thirsty. One has an impact on the other. Conditioning has an impact. Okay, so in our original causal graph, we can see that the two variables, ice cream sales and drownings, are not independent. So when you condition one on the other, actually there is an association. And the reason there is an association is in the graph, there is a path between x and y. There is information flowing from x to y. We are not blocking that path. In order to eliminate that association, we would need to block the path. And that brings to the concept of causality. Causality occurs when this condition happens. So x causes y if the probability of y conditioned on, not on x, but on setting the value of x is different from the unconditional probability of y. What this means is the following. Suppose that we ban ice cream sales. We ban them. Ice cream sales will be 0. Now, weather has no effect on ice cream sales, right? Because we have set that value. And because we have set that value, we are not allowing W to be a confounder anymore. The bridge between W and X has been broken. That is really what blocking a path means. We block a path when we eliminate this flow of information, the path between two variables. So we have pronounced a law that bans ice cream sales. Now, is that going to impact, is that going to prevent drownings? No. Okay, so now we know that setting the value of x has no effect on y, therefore x does not cause y. Now that we have done this intervention, we have set an intervention, we have intervened, we have set the value of x, now we can say that x doesn't cause y. What I want you to pay attention to is these two expressions appear to be similar. They are deceitfully similar. The difference is this interesting operator called do. Otherwise, they would be essentially the same, right? They are two conditional probabilities. The difference is this. We add that do operator. And what that do operator means, and I'm sure you have not seen it in your statistic classes because it's kind of a new invention over the past maybe 20 years or so. This do operator, what it says is that we are not conditioning on variable x, we are setting the value of x. The value of x is no longer observed, but we have intervened. We have interacted with the data generating process, and that allows us to remove that arrow and see what happens. And what we say is causality is a very special type of association. It's a very special type of association where the association survives intervention. If the association survives the fact that we have blocked the non-directed paths, once we have blocked all the non-directed paths and the association survives, then we talk about causality. Causality is a very special type of association. It meets these three characteristics. Number one is interventional. It is not an association where causality is not the type of association where we just observe data passively. To decide whether X causes Y, we must have access to either to the data generating process or to be able to interact with the data generating process. So from that perspective, the first difference between causality and association is that causality is interventional. We are actors in an experiment. We are not just passive observers. We need to be able to interact with the process. Number two is asymmetric. Associations are symmetric. Correlations are symmetric, right? Correlation between X and Y is equal to the correlation between Y and X. You look at the function, the equation of the estimator of correlations, and it's clearly symmetric. Not causality. Causality is asymmetric because it follows the direction of arrows. That X causes Y does not mean that Y causes X. And third very important characteristics is that causality is sequential. X must happen before Y. All right, so these are three characteristics that causality inherits from the fact that it is defined this way. So I think that now, whenever someone talks to you about causality, the first thing that you will do is you will try to map what is the causal graph that person has in their head, or in their head, right? You will see that someone tells you, well, the reason this has happened is because that person did that. Okay, let me check the causal graph. Is that arrow in the right direction? What would be the experiment that would allow me to determine that this is really the cause? What path I need to block in order to determine whether there is still association that survives blocking of the undirected paths. So now you have a way of answering causality questions in a formal way. Now, we have a formal definition of causality, but when we deal with investing, we have four very important problems to overcome. Number one, barriers to experimentation. There are very few cases in finance where we can actually block paths or set values. We cannot go back to the flash crash of 2010, remove a couple of traders and see what happens. We cannot go to the great financial crisis, remove Lehman Brothers and see if we would still have a crash. So there are some cases where we can conduct experiments in finance, for instance. Many brokers randomize order flow and they send it to random markets, exchanges, in order to see whether certain algorithms perform better under certain conditions. And that allows them to decide what causes an algorithm to outperform others. So there are some cases where you can conduct experiments in finance, but they are relatively rare. The second problem is non-stationarity. Financial systems are incredibly dynamic. And as a result, the data generating process is evolving all the time. There are either structural breaks or drifts in parameter that means that observations are not comparable. That's really what non-stationarity means. There is a mathematical definition of that, but really the intuition of non-stationarity is, are the observations comparable? Are they all drawn from the same distribution? And that's the reason we set up an ADIA Lab data science tournament to detect structural breaks. Problem number 3 is the signal-to-noise ratio is very, very low in finance. And there is a very simple reason for that. There is a limited amount of mispricing, and many people compete to monetize those mispricing opportunities. As a result of that, signals need to be almost imperceptible, because if they were perceptible, someone would take advantage of them. So the more people compete for this limited number of opportunities, the lower is the signal. So the signal-to-noise ratio is endemically low in finance. That's not true of other fields. For instance, when Einstein published Einstein published the theory of relativity continued to work. When Newton published the Principia Mathematica, gravity still works. I mean, we are still attached to the ground. But that's not true in finance. In finance, if Newton published in finance the equivalent to the Principia, we would actually levitate. We would, the system would change. And that makes very difficult to identify signals that are robust. And problem number 4, samples are very small. We do not have billions of drivers. We do not have billions of photographs where we can train an algorithm for recognizing faces. We have data sets that are short, and even if they appear to be long, guess what? The data generation process has changed. So for all these reasons, applying a statistical analysis to investment problems is particularly difficult. Does that mean that we should give up on applying quantitative methods? No, on the contrary, we need to model that uncertainty, right? The fact that the problem is challenging doesn't mean that we should not use math. It means that actually we should use more math to replace the missing data with a structure. And that's really what causality does. Causality allows us to inject a structure on a problem that is ill-defined, a problem where there is a lack of data, and that lack of data, that lack of information needs to be supplemented by something. And that is what causal models do. Now, there are 2 types of spurious results that we find when we apply mathematical models in investment. The first type of spurious result is what I call type A. And this is the old school overfitting. What this plot shows you is that the expected value of the maximum Sharpe ratio, meaning the efficiency of your investment, increases as a function of the number of backtests that you run. You run 0 backtests, and the expected Sharpe ratio, or 1 backtest, the expected Sharpe ratio is 0 if the true Sharpe ratio is 0. Right? If there is no effect, there is no investment opportunity. You run a backtest, randomly the expected value of that backtest is 0. I mean, that doesn't mean that that's what you're going to get. Sometimes you will get 1, sometimes -1, sometimes 0.5, sometimes minus 0.7. On average, you will get 0 with 1 trial. But as soon as you are running 10 trials, the expected value of the maximum Sharpe ratio will be around 1.7, where the variance of the Sharpe ratio itself was 1, right? As you increase the number of trials, this line goes up and never stops going up. There is no number above which you can say you are safe. Yes, this Sharpe ratio is so high that it doesn't matter how many backtests I run. No, it will keep going up. What this tells you is that you could run enough backtests to achieve any Sharpe ratio. So let's say that someone tells you, I need a strategy with a Sharpe ratio of 5. And you say, sure, just give me the cluster. And it will probably take me 2 million simulations, but, well, actually, how many? Well, about 1 million simulations. It will take me about 1 million simulations, and I'm guaranteed. Actually, it's not a matter of luck. I'm guaranteed. I know mathematically that I'm going to get you a strategy with a Sharpe ratio of 5 in the backtest. Then you put it in production, and it will be 0 if you're lucky. So that is what is called the false strategy theorem. What it says is that there is no limit to how high your Sharpe ratio can be. You can produce spurious results, and it's just a matter of a computational problem. And then there is type B spuriosity, which has to do with causality. The first one just has to do with running backtests. It's more of an association. You will find spurious associations just by trial and error. Type B is more nuanced. It says that suppose that now there is a real effect. Actually, there is a strategy to be had. If you run some backtests, depending on the specification of your model, you may obtain bias estimates, meaning that you may observe association that is non-causal, and as a result of that, your model will be biased, and as a result of that, you may lose money even though there is forecasting power. So that is more nuanced because even if you increase the sample size, your confidence reduces, and you are not better off, meaning that you can be highly confident about a wrong result. So that's very discouraging in statistics. Typically, we work in problems where the more the data, the better. But actually, if you have your model misspecified, the more the data, the worse, because your confidence bands narrow, but because there is a bias in your model because of this misspecification, now you will be overly confident about strategies that actually could lose money. So that's type B. And this type B can occur for one of two reasons. Number one, you mix up a confounder, meaning you do not put a confounder as part of your features. So in this graph, you can see that X is a confounder to Z and Y. So in this graph, yes, X is a, Z is a confounder here. Sorry, Z is a confounder to X and Y. X is the cause, Y is the effect, Z is a confounder. Once you add it, you are blocking this path, so you're estimating the beta correctly. That's what you want, right? You want to block this backdoor path, and the way to do it, Z is a confounder, so you need to add it to your regression. However, if Z is a mediator and you put it, you're blocking one of the two legitimate paths between X and Y. Yeah, you will estimate the beta correctly, but you will not estimate gamma. So depending on the role of the variable in the graph, you need to do one or the other. But if you have a confounder, you need to add it as a feature. However, if you have a collider, you cannot add it as a feature. You can see that in this graph, Z is a collider. Once you add it as a feature, now you open this path. You are no longer estimating beta. Once you add it, you are actually estimating, you are biasing beta by gamma and delta. And that's what is called Bergson fallacy. So my favorite example of Bergson's fallacy is when people tell me, whenever I see a police car, there is a traffic accident, as if it was their fault, right? Why is it that policemen are always bad news, right? Maybe we should defund police because then there wouldn't be traffic accidents, and no, well, actually the police is there not because they caused the accident, but because an accident has taken place. In fact, probably removing the police will make things worse, right? Because there will be more accidents and more crashes as a result of the crash that has occurred. So collider bias is very, very bad. If you mix up a collider for a confounder, typically that flips the sign of the relationship, and you end up buying what you wanted to sell and selling what you wanted to buy, which is pretty bad. One thing that we need to avoid is what is called specification searching. Many econometrics textbooks literally teach students the so-called kitchen sink approach. And what this means is that give me all the variables that you think are relevant in order to predict a variable y, and then apply an algorithm for choosing those variables. And this creates a lot of problems because the thing is, colliders improve forecasting power by taking advantage of non-causal paths. As a result, whenever you add a collider to your model, the adjusted R-square always goes up, and your p-values will always go down. So if you try specifications where your collider is a predictor, everything looks better, when in reality, everything will be worse. It can flip the sign of the betas. That's problem number one, so you will end up buying what you should be selling and otherwise, the other way around. And also, you will engage in risks that are unrewarded. Why is risk Z unrewarded? Well, because the effect has already taken place. How can you monetize something when the one thing that you wanted to monetize has already happened? So you are hedging a risk that for sure it's unrewarded. And by hedging that risk, now you are biasing your betas that decide the exposure to the rewarded risks. And colliders can be so pernicious as to flip the sign of the beta. So you can see from this that specification searching is very dangerous. You should not try specifications before you have a causal graph. But you will not find a single textbook in econometrics, I would say as of last year, maybe one has been published recently without me knowing, but you will not find a single textbook in econometrics that explains the need to understand the role of variables before one chooses any specification. Typically, the standard in econometrics is run a number of combinations and maximize the Sharpe ratio. I can tell you that because, for instance, Eugene Fama won the Nobel Prize maybe 3 or 4 years ago. And in the 2015 paper by Fama and French, where they expand their factor model from 3 to 5 factors, the explanation that they give in the paper for adding 2 additional factors is that it improves their adjusted R-square. So even Nobel Prize winners make this mistake. It's just that there is a disconnect still between econometric practice and causal inference. The recent discoveries in causal inference have not made it to the classroom, much less to textbooks. And that's one of the reasons people lose a lot of money. So, the research protocol goes like this. You have a data set. Given this data set, either you write down a causal graph that makes sense based on your understanding of the markets, or you use a causal discovery algorithm that gives you the causal graph that is consistent with the data. Given this causal graph, you want to monetize a particular forecasting power, a particular cause that generates an effect. You want to monetize that, And depending on the role of the variables, you know, the causal graph tells you what should be your features. And here the goal is to avoid adding colliders to your features. That's it. That's the protocol. The traditional protocol would be try many different combinations and whatever maximizes the adjusted R-square, that should be your model specification. And what this talk tells you is actually not. That can be very dangerous. What you should do is you should come up with a causal graph either driven by theory, possibility number one, just use economic theory and your understanding of the markets, what really makes sense as a potential causal graph. Or number two, also your knowledge of the data, how the data was gathered, etc. Or option number two, you do not want to draw your own graph. Let's use an algorithm that gives you the graph. Or a combination of the two. You use a causal discovery algorithm to draw the graph for you, and then you assess which of these graphs makes more sense given your understanding of the data generating process. And there are many different algorithms for that. I'm not going to discuss all of them. I'm just going to visualize how one of them works, the so-called PC algorithm. The PC algorithm is, the name stands for their authors, Peter and Clark. So it's not named after their last names, it's named after their first names. And it works like this. You have a particular graph. This is the ground truth, right? This is the true, let's say that this is the graphical representation of the data generating process. You do not know that, but you have an algorithm that starts by considering all possible connections. So the PC algorithm starts with a complete graph, undirected, and then it starts by removing edges where there is either independence or conditional independence. So for instance, you know that the ground truth is on the top left, and this is what the algorithm tries to figure out. So why did the algorithm remove the connection between VC and C and E? Well, you can see that because there is no path between these two. There is no directed or undirected path to connect these two. A in the ground truth is a collider, so that path is blocked, and therefore the connection between V and C will appear independent in the data, and the algorithm says, let's remove that. Then it will remove the connection, for instance, between C and D, D and B, and D and E. Why did it remove those? Well, because conditionally they are independent. Once you condition on A, as you can see, A is a mediator between C and D. Once you condition by A, C and D are independent. So the algorithm is using the rules of blocking paths to figure out what relationships are causal and what relationships are not causal. Okay, so now we can remove these three connections. And now it does something very interesting. It says, for a triad of three variables with no edge between x and y, if x is independent of y and x and y are not independent condition on z, then we have a collider, right? We know that once we control for a collider, a block path unblocks. So the algorithm uses that statistical fact to figure out the direction of the remaining arrows. So we said that A is a collider, and we can figure that out because once we condition on A, all of a sudden, the two variables that appear to be independent are no longer independent, right? But we know that paths are blocked when we condition for something that is not a collider. Whenever we condition by something and a path opens, we know that that's a collider. So that's how the algorithm figure out the direction of these two arrows, and those two arrows too. So what remains cannot be a collider, and if it stands in between, it must be a mediator. So now it figures out the direction of these two arrows. In the end, there will be one connection that the algorithm cannot figure out. The algorithm has its limitations. It can figure some directions will remain undetermined. So the algorithm cannot figure out that B influences E. So the algorithm will just tell you, well, that's how far I can reach. For the remaining arrows, you have to figure it out. You have to use your actual expertise. But think what this means. We have gone from a situation where we were clueless, like this, to a situation where we do not know this one, but otherwise, everything else is well understood. So we have been able to inject a lot of information to the model that now we can use to decide our specification. Okay? So this is not limited to finance, of course. For any empirical analysis, now you have the tools to decide your model specification. Now, I invite you to check the large majority of papers published in statistics, and you will barely find an explanation like this. So again, this is something that people have understood recently, but not even textbooks or even journal articles are familiar with. And it has created a lot of issues. For instance, you may know that around the year 2011, I think, the year 2011, Perlmutter and other people were awarded the Nobel Prize in Physics for discovering that the expansion of the universe was accelerating, and that was massively celebrated. Well, in September of last year, someone figured out that there is a problem with this statistical analysis. Right? They collected data from multiple observatories around the world, and they figured out that the universe must be accelerating because the redshift was stronger than what would be expected of a universe that is not accelerating. So as you know, the redshift occurs when the universe expands, and as a result, the wavelength is much more stretched than what would be expected, and that led researchers to figure out that, well, look, it must be that the universe is accelerating. And that led to the theory of what is called dark energy. There is an energy in the universe that is pushing, stretching the universe even faster than what would be expected simply from the Big Bang. Okay? So last year, a team of researchers came up with the following. Well, that assumes that galaxies, the supernova that occurs in a galaxy, the explosion of a star in the galaxy, generates a certain light intensity regardless of when it occurs. But what they discover is that there is a confounder in the model. Good. There is a confounder in the model. Today's supernovas are dimmer. They produce less light intensity than supernovas that occur millions of years ago. And this confounder, which was not taken into account in the model, biases their estimates such that the new belief is that the universe is not expanding at an accelerating rate. It's expanding at a constant rate. There is no acceleration in the expansion of the universe, which means that there is no need for dark energy, which, by the way, nobody has been able to find. So what I'm telling you is that causality is becoming extremely important at all empirical work. And when you have Nobel Prize winners like Perlmutter in physics or Eugene Fama in finance, where they make literal statistical mistakes because they never care to draw a simple causal graph, that tells you that this is a problem that permeates to the highest level of science. Okay, conclusions. We can rank empirical evidence based on the following axis. Someone gives you an expert opinion, and that's really at the bottom, because no matter whether someone is an expert or not, it's just their opinion. And you have an opinion, I have an opinion, and it's not, we can disagree. The next level is case studies, which essentially means that someone provides an elaborate theory or explanation as to why something happened. But this theory is not really supported by a large amount of evidence. Maybe it's a theory based on a particular case, like for instance, a case study on the collapse of Lehman Brothers. Okay, so the guy will make a lot of theories and potential explanations, but it's just one case. The next one is, I would say, 99% of empirical studies. These are associational studies, like the one I mentioned before, Perlmutter or Fama. Essentially, someone runs several associations and there is a forecasting power, but there is actual, and then they will have a causal statement that is unsupported by any sort of theory, because as soon as people are able to predict something, they get really excited. They really believe that whatever is a predictor must be a cause, which, as we have seen, is absolutely not the case. The next level will be simulated interventions. This is the case where you cannot conduct an experiment, but you can simulate an experiment. And this is really what we do when we have a causal graph. When we do a causal graph, we say, well, suppose that the data is generated by this. Let me condition on this confounder, then I can block the path, and that will allow me to estimate the effect that I would get in a laboratory if I were able to interact with the data generating process. So that's the next best thing. It's not as good as a randomized control trial, but it's really almost as good as that. Above simulated interventions is what we call natural experiments. This means that rather than us doing a random assignment of subjects to treatments, like in an RCT, like in a randomized control trial, what we do is we use the fact that nature has done the randomization for us. And that happens sometimes, for instance, with lottery winners. There are several instances. For instance, suppose that there is two towns that are at the border of a state, and the fact that one town is a few meters from the other, and there is a frontier between two states, is really random. I mean, there was probably the cities were established and they grew before the states were created. So it's really like a random effect. It's a random assignment of the cities to the states. And the fact that they are very close, very likely they are influenced by the same economic factors. Really, the differentiating factor is that whether one was assigned or not to a state. So that's an example of a natural experiment. The two towns are essentially indistinguishable from each other, except for the fact that one belongs to a state. And that allows us to make comparisons and evaluate whether certain policies have an effect, are a cause of certain effects. And then the top of the hierarchy would be randomized control trials, which are sometimes not possible. Sometimes they are possible, but they would be unethical or illegal. For instance, human experimentation is possible, but we would object to that. And sometimes they are possible and legal, but they are too expensive. For instance, the development of antibiotics. Society has developed very few antibiotics over the past 20 years because they are really, really expensive. And once you develop them, even though it costs billions of dollars, you can use it very limited because, as you know, the more you use an antibiotic, the less effective it becomes. So that's the ranking of evidence. Most of the times, studies are here. They're associational studies, but now you know how to reach the next level. To reach the next level, to avoid joining this crowd, what you can do is you can justify your model's specifications with a causal graph. That is the way you are disclosing to your readers why you chose a particular model from purely a conceptual perspective, not just because some associations misled you into that specification, but this is what really justified that you chose that specification. So with that I conclude my talk, and I look forward to your questions. Thank you.
Thank you very much, Marcos. We are, sorry. Thank you very much, Marcos. We are over time, but Marcos has the transfer to the report just now. We have only one question and quick answer.
Yeah, one question. That's good.
Natalia, for you, the prize.
Thank you so much, Marcos. So,
elevate the voice because people must listen.
Yes, thank you so much for the very thorough question. Yeah, my question is related a bit to yesterday's question, like how can we simulate actually all this, as the graphs can never be grounded in real data. What is, in your opinion, the best simulator? Are digital twins? Because, you know, simulators are, in the end, simulators. What would be, in your opinion, the best way to approach simulated worlds in order to ground this lack of data?
Yep, very good. So in order to simulate a state of nature, you need the causal graph, right? So the causal graph is really the representation of the data generating process that allows you to decide what is the role of a variable in the system. So the starting point would be a causal graph. You can reach that characterization of the process in two different ways, at least, right? Number one is from first principles. You understand that this variable cannot potentially be a cause. Like, you know, what is the price of butter in Bangladesh a potential? Would it have a potential influence on the price of, I don't know, Netflix? Probably not. And even if there was a connection, probably is very small. So there are just some basic first principles that inform what variables would form part of the system. So that's one avenue. The second one is we can use causal discovery algorithms to try to identify what is the potential family of graphs that are consistent with some empirical evidence. So now that you have a causal graph, we can simulate what happens if this parameter changes value, right? So for instance, here in this example at the beginning, I played with delta. I said, well, what happens if I start with delta 1 and I move it to 3? If I have the incorrect model specification because I added a collider to my features, the beta flips from 0.5 to minus 0.5. And as a result, I end up buying what I should be selling and selling what I should be buying. So this allows you to simulate the scenarios, right? Given that this is the data generating process, what happens if I remove this arrow, which means delta is 0? Or what happens if I weaken the effect, or if I increase the effect? And that allows you to generate new data, and you can see how your system reacts to this new data. How robust is your system to the new data? And I thank you for this question, because it allows me to say something that I had not said. When we correctly identify Z as a collider, we will not add it to our model. Because we have not added it to the model, delta doesn't matter. So even though I have less forecasting power as a result of, actually less forecasting power in sample, my statistics will look worse. Once delta changes, my strategy keeps going up. Why? Because I have exchanged spurious forecasting power for robustness. Z was never a true predictor. Only in sample, only when I run the regression, appeared to be a good predictor, but in reality, because it is a collider, it's not a predictor. In fact, it's a consequence. Because I have not added it, once delta flips, my strategy keeps going up. It's unaffected. If I had just developed my strategy without a causal graph, I would have added Z, because my adjusted R-squared would be higher, my p-value would be lower. I would be very happy in sample, very unhappy out of sample.
Thank you.
Thank you very much, Marcos.